Okay, and welcome to a new series of videos where we'll be focusing on Mechanics 1, an integral part of the applied course, obviously with Statistics 1 for Year 12, and obviously following into Mechanics 2 and Statistics 2 into Year 13. So in the first video we'll be looking at modelling and assumptions, and this is an important part of the mechanics thought process in both Year 12 and Year 13. So let's get straight into it then. Now you've already seen modelling before in Pure 1, quadratic modelling, straight line modelling, and you'll continue to see models in the Pure course and going into statistics. A mathematical model is basically an equation which describes a real life problem. Models are used everywhere in most real life situations. A good mathematical model is one where the equation is as simple as possible but still gives reasonable answers. As mathematicians, we like models to try and fit as much of the data as possible, or to try and be as realistic as possible. So in front of us we have here a model of the motion of a basketball as it leaves a player's hand and passes through the net. And it can be modelled by this equation, h equals 2 plus 1.1x minus 0.1x squared. Now clearly we can see on the face of it that this is a negative quadratic. So we know that it's going to have a shape that looks like this, which makes sense because as a basketball is thrown up in the air, it's going to have that sort of motion as it goes through the net. Okay. Anyway, h represents the height of the basketball above the ground, and x is the horizontal distance travelled. So you've got to understand this. H represents the height of the basketball above the ground, and x represents the horizontal distance travelled. So part A, it's saying using the model, find the height of the basketball when it's released. Now if you imagine when the basketball is released, here's the basketball. Okay, there's the person about to throw it. There's the ground. So obviously a fairly crude diagram. When the basketball is released, what we're going to assume at that moment at which it's released, that it has travelled a horizontal distance of 0. Okay, so when it's released, time is equal to 0. But obviously we're going to assume that the horizontal distance travelled is also equal to 0. So what I'm going to do is I'm going to sub x equals 0 into the model. So when I do that, I'll get a value of 2 meters. So the height of the basketball when it's released is 2 meters, which sounds appropriate given the average height of a person, an adult player would be, 6 foot, roughly 2 meters, and obviously you got the height from the hand. Then it's saying at a horizontal distance of 0.5 meters. So what's happened now is the ball has travelled a certain horizontal distance of 0.5 meters across. So what we've got to do is sub x equals 0.5. Okay, and when you do that, you get 2 plus 1.1 times 0.5 minus 0.1 times 0.5 squared. Okay, now if you quickly use your calculator for this calculation, you get 1.1 times 0.5, so you get 2 plus 0.55 minus 0.5 times 0.5 times 0.1 minus 0.025, and then what you're going to get is 2 plus 0.55 minus 0.025. Okay, which makes sense because when the basketball has been thrown, obviously it's going to have this sort of path, then it's going to have travelled further up in the air as it travels further across horizontally. So that's fine. Use the model to predict the height of the basketball when it's at a horizontal distance of 15 meters from the player. So they're asking us to find the value of h when x is 15. So again, you just substitute x equals 15. You're going to get 2 plus 1.1 times 15 minus 0.1, 15 squared. Now, what you'll notice is that 15 is a much larger number compared to what we put in before, 0.5 meters. So let's just see what happens there. 1.1 times 15, so you can get 16.5. Then you've got 15 times 15 times 0.1, 22.5. So you're going to get 2 plus 16.5 minus 18.5 minus 22.5. You're going to get minus 4 meters. Right, so let's just try and understand this. Comment on the validity of the prediction. Now, validity means how good is the model, how valid is the model up until, is the model valid for a certain range of x values? Can it be extended to all x values or positive x values? Depends on the context. Now, if I sort of think about it on part B, when the ball, use the model to predict the height of the basketball and its horizontal distance of 50 meters from the player. So, you know, if I had the ball, there's its motion. Now, remember, the height when it was thrown was 2 meters. Okay. Now, suddenly, 15 meters across from where it was thrown, it's minus 4. Okay, so suddenly the ball is in the ground, which obviously is not realistic. So the model is not valid for larger values of x. So the model is limited to much smaller values of x, 1.5 meters, maybe 2 meters, but as soon as it hits the ground, it's not able to sort of give an answer for, you know, what happens after that. So the model is not valid for larger values of x. Okay, so every model has a limitation. Okay, as mathematicians, we try and get a perfect model, but it doesn't always happen. Okay, so here, this flow chart at the bottom, this summarizes the process. We have a real world problem. We set up a model, and as mathematicians, we like to have assumptions, and we like to think of the variables. We solve and interpret, so we carry out the model, like we've done here. We think, is our answer reasonable? If it is, then we report a solution. If it's not, we can reconsider our assumptions and work through the loop, okay, until we get a reasonable answer. So that was a quadratic model, okay, and obviously there are some exercises at the end of this page here, page 119, exercise 8a. I would also like to have a look at some modelling assumptions, which are on the next page in the workbook. Okay, so mathematicians like to use these assumptions to make our models a lot more easier to deal with, but to also disregard any information that we don't think is important. Okay, so here are some common models and modelling assumptions that you need to know. So I'll work for each of them. I mean, that these are things that you definitely need to know through the mechanics course. So words in bold will come up throughout mechanics 1 and 2 in year 12 and year 13. So whenever you see the word particle in mechanics, it's a modelling assumption. Whenever you see the word model, a particle inside a model, it basically talks about an object where the dimensions are negligible. So basically, a particle, we could have, in the previous question, we could have modelled the basketball as a particle. We don't care about what the basketball looks like, its surface, or anything like that. But most importantly, why do we use a particle to model in a certain situation? Because we assume that the mass of the object is concentrated at a single point, and we don't care about rotational forces or air resistance. The next word that the next sort of type of model that you'll definitely see is one which involves a rod. And this is a one-dimensional sort of setup, like a pole or a beam. Okay. Again, why is this important? Why is this helpful for us in terms of assumptions? If we assume something is a rod, we assume the mass is concentrated along a line, we assume there's no thickness, and we assume it's rigid, i.e. does not bend or buckle. A lamina, not very common across the mechanics course, but nonetheless it is there, is an object with area but negligible thickness, like a sheet of paper. We assume if we say anything's a lamina, we assume the mass is distributed across the flat surface. Uniform body is something that you'll definitely see quite a lot of. If you ever see that in a mechanics type question, then what we do is we assume that the mass is distributed evenly. Okay, and not only that, the mass of the object is concentrated at a single point, and that single point is at the geometrical center of the body, the center of mass. So if I have a uniform body of 2 meters long, it could be a ruler. I'm going to assume the center of mass is bang in the middle of that ruler. Light object. A mass of the object is small compared to other masses like a string or a pulley. We treat the object as having 0 mass, and the tension is the same at both ends of the light string. So you might see this when you do pulleys. Another thing that you'll see doing pulleys is inextensible string. So an inextensible string is a string that does not stretch under load. So we do not take into consideration how it stretches, and we assume that the acceleration is the same in objects connected by a taut, inextensible string. Okay. And the next couple you definitely see during the course: smooth and rough surface. A smooth surface is such that we assume there's no friction between the surface and any object on it. A rough surface is obviously the opposite. Okay, objects in contact experience a frictional force if they're moving or acted on by a force. A wire, again, it's a rigid thin length of metal. We treat it as one-dimensional. A smooth and light pulley, you'll see this in Mechanics 1. All pulleys you consider will be smooth and light, i.e. the pulley has no mass, that's the light aspect, and the smooth tension is the same on either side of the pulley. A bead, again, not very common across the course, neither is a peg, but the assumptions are there. Air resistance, definitely something that you'll come across. Resistance experienced as an object moves through the air, usually modelled as negligible though. And gravity, which is a force of attraction between all objects. Acceleration due to gravity is denoted by g. Okay, so, and obviously there is a gravitational constant which is 9.8 meters per second squared. We also assume Earth's gravity is uniform and acts vertically downwards. Okay, and that's really it in terms of the assumptions.